In this video, I'm going to discuss a quiz that we had that was covering chapters 3, 4, and 5. In this video, let's begin by looking at questions 1 through 5. Here's the first question. We're combining aqueous solutions of lead nitrate and potassium iodide, precipitate forms, and we have KNO3 left over in solution. 1 mole of each of the reactants is being combined, and we're asked what's left after the reaction. If we want to keep track of things, since this is a stoichiometry problem, I would use a BCA table. We have the initial amounts of both of the reactants. Which one's the limiting? Let's just choose the lead nitrate. If we use up 1 mole of the lead nitrate, we would need 2 moles of the potassium iodide, but we don't have 2 moles of the potassium iodide, only 1. So the potassium iodide is the limiting reactant. If we use up all 1 mole of that, we can see based on the change line that we would use half a mole of the lead nitrate, we would form half a mole of the lead iodide, and 1 mole of the potassium nitrate. Remember that the ratios within the change line are the same as the ratios within the coefficients of the balanced chemical equation. Afterwards then, we can simply combine the before with the change to see what we're left with. Now this question is asking, okay, tell me something about the concentrations that we're left with after the reaction. Well, if we look at the lead nitrate, that's an aqueous solution. It's a strong electrolyte, so it's going to dissociate, and if I have half a mole of lead nitrate, that means I have half a mole of lead ions and 1 mole of nitrate ions. If we can carry on within the other ones, we see that the solid, it is not a strong electrolyte. It's the precipitate that's being formed. All of the Ki, when we account for it as a reactant, was used up, and we can see the amount of potassium nitrate that formed. So now if we look at these and analyze these, we can see that in terms of the concentration, the nitrate and the potassium concentrations are not the same, nor is the lead or the iodide, and then finally the nitrate and the iodide. All of the concentrations are different. We were able to keep track of this by seeing within our BCA table what we were left with after the reaction, and we considered both on the reactant side and the product side what was in the beaker. You might have a different approach for this. Is there a shortcut or a different way that we can think about it? Well, within our BCA table we can again determine what the limiting reactant is. If we consider the net ionic equation, lead ions and iodide ions are combining to form the lead iodide. Ki is the limiting reactant based on the mole amounts because all of the iodide ions are being used up. We can also observe that both the nitrate and the potassium are spectators and their mole amounts do not change. So we can see right away that we don't have any aqueous iodide ions. So there's no way that we could consider them to have an equal concentration with something else at the end. Similarly, the potassium and the nitrate concentrations, well, those mole amounts were not the same to begin with, and since they're spectator ions, they will not be the same at the end. Here's another question. A conductivity probe with the light bulbs inserted into different solutions, which produces the brightest light. We described a conductivity probe as being a free ion detector. So we want to say how many ions are present in each of the solutions. Which solution provides the highest concentration of aqueous ions? That would be the brightest light. So we need to classify these. These are discussed in chapter 4. We have examples of strong electrolytes because they are ionic. That's both the sodium chloride and the calcium chloride. A non-electrolyte, which was sugar, and a weak electrolyte, acetic acid, which is a weak acid. If we look at the strong electrolytes that are ionic compounds, the sodium chloride dissociates and gives me 1 cation and 1 anion. The calcium chloride, however, gives me 1 cation and 2 anions. If they both begin at 0.10 molar solutions, I have more ions in the calcium chloride. It will produce the brightest light. This one's involving activity series data, and some information is provided, and we're trying to see which of these, when it reacts with HCl, leads to the formation of H2 gas. So we want in chapter 4 to be able to apply activity series data, interpret it, and see what's going on. let's look at choice A. It says that we can take metal X, which is a solid, and we're putting it in a solution of HCl. That's saying that we're putting it in a solution that has H plus present. So this is the comparison that we're making. Notice the metal is above the ion. The metal is, in this order, the most easily oxidized. At the bottom, most easily reduced. So within this combination, what would we observe? The metal would indeed be oxidized, and the H plus would be reduced to form H2 gas. What would we be observing in the beaker? Bubbles of H2 gas would form as the metal dissolves. What if we consider option B? Within option B, there's no reaction. The metal has already dissolved and exists as the X plus aqueous ions in solution. For both C and D, also no reaction. They are below the H plus on the periodic table as either the solid or as the ion. So option A is correct. Which of these is a strong electrolyte with a low solubility in water? So first of all, we want to be able to classify these. Okay, this is from chapter 4, and we're combining the ideas of solubility and also descriptions like acids and bases. Acetic acid is a weak electrolyte, not a strong electrolyte. We have examples of ionic compounds and a molecular compound, HCl, that is a strong acid. How do we know it's a strong acid? There are 7 strong acids we want to memorize. What does it mean then to have a strong electrolyte with a low solubility in water? Let's now consider the solubility rules. Sodium is a very soluble cation. So I'd say sodium hydroxide is a substance not with a low solubility but a high solubility in water. The chloride, it's also quite soluble unless it's paired with an insoluble cation like the silver plus. Therefore, we could consider AgCl to be a strong electrolyte that also has a low solubility in water. We saw a particle level description of this. Something like NaCl would be shown there on the left. We have a strong electrolyte, meaning we have cations and anions, not molecules present. And a lot of the sodium chloride can dissolve to give us those cations and anions. On the right, that's an example of something like silver chloride. We once again would call it a strong electrolyte because we do not have molecules present. However, far less of it dissolves. This is an enthalpy question. We're asked to calculate an enthalpy change for a target reaction, and data are provided. This is definitely an example of Hess's law. We're going to want to manipulate the 3 equations to result in the target equation. What is the strategy for this? I would look to say what features in the target equation are unique in the provided equations. So for example, C2H4, it shows up in the target equation and only in one of the provided equations. So I know if I put that equation where the C2H4 is in the correct spot, it absolutely has to be right. You notice within several of the provided equations you have O2 gas showing up. That's going to be very difficult to anticipate how it will cancel out. Don't begin with something that appears in several of the equations. Begin with the unique features. Those are all shown here in red. The first equation I can list as is because I want to have C2H4, 1 mole of it, as a reactant. That's how it is in the provided equation, and that's how it shows up in the target equation. The C2H6 gas, I also want 1 mole of it, but I need to reverse the reaction, so therefore I change its sign. The H2 gas, I want 1 mole of it, and as a reactant, so that was also in the right position. So the only thing I had to do was reverse the second reaction. When I add them all together, it results in the target equation, and I add up the delta H values to get the overall enthalpy change. These are the first questions from the quiz that covers chapter 3, 4, and 5. Check out a second video to see questions 6 through 10.